Okay, let's do this again. 17b. We talked about erythropoiesis and how it's an avenue of hematopoiesis, the production of erythrocytes. Well, the production of leukocytes is called leukopoiesis, and it is stimulated primarily by a couple of chemical signals, interleukins, which, if I remember correctly, we'll come back to in a different chapter later, and colony-stimulating factors, which we'll also come back to later. The hematopoietic stem cells that give rise to all formed elements, they differentiate into, initially, either myeloid stem cells or lymphoid stem cells. And myeloid stem cells are the stem-like cells that give rise to almost all formed elements, and we'll specify which in just a moment. But the lymphoid stem cell line is what gives rise specifically and only to lymphocytes, so B cells and T cells. And if we look at the next slide, this diagram, which initially scares the holy hell out of us because it's got so many words and labels. The good news is that I really only need you to know which formed elements arise from which stem cell lines. So really the eosinophils, the basophils, the neutrophils, the monocytes, and for that matter, indirectly, platelets, directly megakaryocytes, and of course erythrocytes, red blood cells. They all arise from the myeloid stem cell line, okay? Whereas the lymphoid stem cell line gives rise to lymphocytes. And B cells and T cells can in turn differentiate into other cells, but once they're B cells or T cells, they're committed to that line. They can't ever differentiate back into something that would have come from the myeloid stem cell line. So most formed elements, again, myeloid stem cell line, the lymphocytes are the exception. We've already established that different formed elements live for different lengths of time. Platelets are very short-lived. We just established that at the end of 17A. Erythrocytes, we know, can typically live for up to 120 days. Monocytes, they stick around for usually several months. And lymphocytes, it all depends on which lymphocyte we're talking about, so and how differentiated that lymphocyte is. Sometimes a lymphocyte will only survive for a few hours, and then there are other lymphocyte derivatives that survive for decades, and we'll learn later that one of the lymphocyte derivatives are collectively called memory cells, and it's typically the memory cells that are going to survive for decades. We want that wanted poster to stick around for long enough so that we can recognize the bad guy if we ever meet him again. Leukemia is yet another blood disorder to put on our list alongside anemias and polycythemias, and maybe even some of the leftovers from chapter 19, the vessel chapter. Leukemias are an umbrella, or leukemia is an umbrella term for really any cancerous condition that yields the overproduction of not just white blood cells, but faulty, abnormal white blood cells that can't do their job. And so this is a little different than just saying in general leukocytosis, which is certainly a big production of white blood cells, an excess of white blood cells, specifically over 11,000 white blood cells per microliter. But just because a patient exhibits leukocytosis doesn't necessarily mean that they have leukemia. Leukocytosis doesn't necessarily equate to an excess of abnormal leukocytes. And leukemias will often involve the cloning of an abnormal origin or an abnormal parent cell. And often in biology classrooms, I find that students don't have a clear understanding of what the word clone means, at least in the context of biology. And a clone is just a genetic copy. Despite what you may have been led to believe by the media or through entertainment, a clone is a genetic copy, not necessarily a phenotypic copy, which means that parent and cloned offspring don't necessarily have to look the same. They just have to have the same exact genetic code. Is that genetic code always expressed in the same way? No, not necessarily. And just grain of salt here. We have one slide on leukemias. We could make an entire quarter out of cancer. In fact, we do have a course that's entirely about cancer. So I could go off on so many tangents just from this slide. But the gist here is that these excessive but also abnormal leukocytes will crowd out in bone marrow and, for that matter, in blood, other cell lines, other important formed elements, and render us sort of undersupplied with healthy and normal white blood cells. So crowd out the norm. All right. And often this leads to anemia, makes us more prone to blood loss, aka hemorrhage internally, and obviously more prone to persistent infections because we don't have normal white blood cells to deal with infections. Now, anemia in particular might kind of throw you for a loop because you might be thinking, understandably, wait, Tessa, I thought that polycythemia vera was an overproduction and associated with cancer. Well, yeah, you're right. However, polycythemia vera is associated with bone marrow cancer, not leukemia per se, and it is an overproduction of erythrocytes that are not necessarily abnormal, whereas leukemia is the overproduction of not just leukocytes, but abnormal leukocytes, making way too many copies of a faulty parent. Okay? Now, leukemias are much more prevalent in older patients because older patients have lower reserves, but among the demographic of children and teenagers who are not prone to developing cancer in the first place, leukemias are also the most common type of cancer in that demographic. Hemostasis is a very big ball of wax that it is a series of many steps that help us to cope with the challenge of blood loss. And in the mix are many molecules, many of which are proteins, that are called clotting factors. as well as other substances that are released by platelets and or released by injured tissues. And there are three major steps involved. However, I think that this idea of three major steps involved is a little weak. I would argue there are 5 major steps involved, and those are just major. So I don't know that memorizing a number of steps is really going to benefit you. I think it could actually hurt you. But the first thing that always happens in hemostasis, also be careful, this is not the same as the word homeostasis, although it certainly is an effort to regain homeostasis. The first step, and excuse the way that this slide ends up laying out and looking gross in this particular app, is always vascular spasm. And you probably already think of spasm as repeated contraction of muscle, and that's absolutely what we're referring to in this particular case. Specifically, it's repeated contraction of smooth muscle in vessels. And if vascular spasm has been triggered, then specifically vessels have been injured. So hemostasis always starts with an injury to vessels, meaning circulatory vessels. And when that injury occurs, platelets will typically cling to the site of injury and become activated, and therefore release many of their contents, which we recently learned, serotonin, ADP, and clotting factors galore. But there are also chemicals that are released by damaged endothelial cells, the lining of the vessels, and all of these chemicals help to spurn the rest of the hemostatic process, as well as sort of help to exacerbate our sense of pain, so that we can become aware if that injury is occurring and therefore stop the injury, which doesn't mean repair the injury, just stop the source of damage. And vascular spasm is going to occur in any, just about any damaged vessel, but it's most effective in small blood vessels. Their narrow diameter means the spasm is going to have the greatest and most efficient, what is the word I'm looking for? Good grief. Effect on narrowing that blood vessel diameter, because there isn't a lot to go around. Platelet plug formation is the second step, and you already know that platelet aggregation, which is also the same thing as saying platelet plug formation, is part of a positive feedback cycle that platelets, once activated, in turn activate other platelets. And so it sort of turns into a platelet snowball. The more activated platelets there are aggregated together, the more likely they are to activate other platelets, and so on and so on and so on. And in the case of platelet plug formation, that damaged tissue in the vessel will expose negatively charged surfaces that underlie the endothelium. Usually the endothelium masks these negative charges, doesn't expose platelets to these negative charges, and when damaged, those negatively charged surfaces are exposed, and as a result, platelets that come into contact with those negatively charged surfaces become activated. And activated platelets, they get a bit bigger, they become more angular and therefore more sticky, and they release many of their contents, including serotonin, will further exacerbate vascular spasm or further promote vascular spasm, as well as help to make, again, the platelets sticky. ADP also helps to make the platelets sticky. It helps to activate platelets that come into contact with the plug. And again, as the plug accumulates more platelets, in other words, activates more platelets, any other platelets that come along via the bloodstream that are inactive are more likely to come into contact with activated platelets. Well, it turns out that activated platelets also bear a negative charge. And so activated platelets, even if they're masking a damaged site, they themselves can act as that negatively charged surface that activate other platelets. So here's a ridiculously simple, in fact misleadingly simple diagram of hemostasis, emphasizing our first two steps, vascular spasm and platelet plug formation. And then the third step is really, really involved, and that's why this is so misleadingly simple. And that third step is coagulation. And coagulation can occur via a couple of different pathways. And those two different pathways we'll come to in a moment. They're called the intrinsic and extrinsic pathways. But in either case, we're going to reinforce what we established in step 2. We're going to reinforce that platelet plug, ultimately with interconnected threads of a protein called fibrin, or chains of a protein called fibrin. And during coagulation, the local, not all, because oh my gosh, the local blood will become rather gel-like, which actually facilitates trapping that local site within this clot. And no matter which pathway is used to achieve coagulation, we're going to use clotting factors. And almost all clotting factors are proteins. Almost all of them are plasma proteins, which in turn also means that almost all of them are produced in the liver. And there are many, many clotting factors. They're all named using Roman numerals, which is a pain in the hiney, but a very common theme in AMP2, that we have to use Roman numerals for to identify different substances. And those Roman numerals range from 1 to 13. Now here's the problem. These clotting factors are named in the order that they were discovered, not necessarily in the order in which they function, which is going to be a pain in the hiney. Oops. At least 4 of the clotting factors require availability of vitamin K in order to be synthesized. So if we have a deficiency in vitamin K, then we're likely to not have a full complement of clotting factors, which could be dangerous. In all 2 pathways, again, the pathways are intrinsic and extrinsic pathways. We're going to yield first prothrombin activator, and then using prothrombin activator, we're going to yield thrombin, and then using thrombin, we're going to yield fibrin. So 3 major steps or phases, no matter what pathway. Both intrinsic and extrinsic pathway are going to yield prothrombin activator, thrombin, and fibrin in that order, okay? So again, the pathways are intrinsic and extrinsic pathways. Be aware that usually damage to a vessel is actually going to initiate both pathways simultaneously. Usually simultaneous. Oops, that was messy. Oops. All right. Either intrinsic or intrinsic is prodded by damage, but that's obvious because vascular spasm doesn't occur unless vessels are damaged. And both pathways include clotting factors, involve clotting factors, and both pathways are a cascade, a collection of reactions, one driving the next, toward clotting factor 10. Clotting factor, whoops, whoa, what did I just do? There we go. Clotting factor 10, Roman numeral 10. Okay, so whether it's intrinsic or extrinsic, we're trying to get to clotting factor 10. Clotting factor 10 then will complex with calcium, platelet factor 3, which is not the same thing as clotting factor 3. Gross. And clotting factor 5. And those four things together, 10 plus calcium plus platelet factor 3 plus clotting factor 5 equal prothrombin activator. Prothrombin activator. Okay? So even though we're going to get to factor 10 in a different way, along a different pathway for the intrinsic route than we will via the extrinsic route, they both yield activated clotting factor 10, and then that clotting factor 10 combines with calcium, platelet factor 3, and activated clotting factor 5 to produce prothrombin activator. Okay? Now, the chief differences between the intrinsic pathway and the extrinsic pathway really have to do with where the damage occurs. And the intrinsic pathway, it's stimulated when really the endothelium is disturbed. Okay? And the endothelium being disturbed, therefore, exposes negatively charged surfaces, underlying negatively charged surfaces, which, as you know, sort of calls out to passing platelets. Hey, clump here, clump here, clump here. Okay? Whereas the extrinsic pathway you might think of it as damage from without rather than damage from within. And my brain, I guess being very visual and kinesthetic, I imagine a vessel being crushed in the case of the extrinsic pathway, whereas in the case of the intrinsic pathway, I imagine a boulder, obviously small one, running through the vessels and scratching the endothelium. But again, very, very important. Most damage will actually yield both, right? If a vessel is crushed, for instance, isn't it likely that the endothelium will also be damaged? Sure. Okay? But in the extrinsic pathway, the damaged tissues that surround the vessel, they release a clotting factor. It's clotting factor 3, but it's also known as tissue factor. Tissue factor. Okay? And that starts the extrinsic pathway or extrinsic snowball rolling. All right? The extrinsic pathway has fewer steps, and is therefore the faster mechanism. The extrinsic pathway is more involved. There are more steps, and so it's the slower pathway. Okay? All right, so let's look at how the book lays this out. This is just coagulation. So we're just looking at the intrinsic and the extrinsic pathways, okay? And be aware that just because we yield prothrombin activator doesn't mean that coagulation is finished. We still have to yield thrombin, and then we have to yield fibrin. And then we have to interconnect that fibrin to make a fibrin mesh, okay? So this is really sort of like, I think of this as step 3A. I'll be right back. Okie dokie. So this darker blue side of the diagram, this is outlining the intrinsic pathway. And remember, what initiates this is, there we go. Damage from within, damage to the endothelium, okay? Whereas damage to the entire vessel wall, typically damage from without, so like crushing, even a stab wound for that matter. Okay, for an extrinsic pathway, which is the light blue side of the diagram. All right, we're going to do one at a time though. When we're following the intrinsic pathway first, okay, when endothelium is damaged and exposes the negatively charged underlying surfaces that make up like the remainder of the vessel wall, platelets are going to cling to that negatively charged surface and become activated. And in turn, what they release, they're part of what they sort of express upon activation, is going to help to activate clotting factor. Sorry about this weird typo here. Clotting factor 12. That's the first activated clotting factor in the intrinsic cascade. Activated clotting factor 12 then activates clotting factor 11. Activated clotting factor 11 in combination with calcium, which is going to be a big player for both pathways really, is going to activate clotting factor number 9. Clotting factor number 9 activates clotting factor 8. 9 and 8 then couple. They form a complex. And this complex of activated 9 and activated 8, they are in turn going to activate 10, clotting factor 10. And recall that clotting factor 10 plus calcium plus platelet factor 3 plus activated clotting factor 5 yield prothrombin activator. Okay. Now we're going to march through. Just trying to get rid of, wow, never make dots on there again. That's the take-home message there. Okay, now let's walk through our extrinsic pathway. Our compromised vessel wall will allow chemical signals from surrounding tissues to enter the lumen of the vessel. And one of those chemical signals is clotting factor 3, also known as tissue factor. Tissue factor works with calcium to activate clotting factor 7, activated clotting factor 7, as well as tissue factor. They combine, they form a complex, and in the extrinsic pathway, it's this complex that then activates clotting factor 10, just as with the intrinsic pathway, clotting factor 10 activates 5. There's 10. There's 5. And activated 10 plus activated 5 plus calcium plus platelet factor 3 yield prothrombin activator. I did not learn my lesson about making dots today. Okay? Fewer steps on this side means faster. That is messy looking. Okay. More steps on this side means slower. Now be careful. Both of these are still occurring super duper fast. Very, very, very quickly. Okay? Just a slower version of very quickly and a faster version of very quickly. All right? Now, you probably noticed this arrow connecting extrinsic and intrinsic pathways. Well, if both extrinsic and intrinsic pathways are co-triggered, co-stimulated, then activated 7 not only combines with tissue factor to help activate 10, but it also feeds into the intrinsic pathway and facilitates the formation of, or really activation of, clotting factor 9. Okay? So pretty crazy stuff. And honestly, the only way to get it down is to write it out. However, I personally think there's a cleaner way to write this out, and I'll show you that in class. I'll show you a model in class, okay? All right. Now that we have these two pathways at least established, you'll need practice to really get them down, but established, and we know that they yield the same product either way, prothrombin activator, and we also know that usually both of these guys are being triggered at the same time. Now we can move on to what I might call step 3B. And again, you might call this 3A. If you really need to give a step name to all of these horrible events. Well, in the case of this next step, what I just called 3B, our product from intrinsic, extrinsic, or both pathways, prothrombin activator, it's going to act as an enzyme, as a catalyst to in turn activate thrombin, or really activate prothrombin yielding thrombin. Thrombin is the active form of prothrombin. So this is inactive, this is active. Now that we have thrombin, we can move into our next step, which you might call 3C if you need a step name. And now that we have thrombin, activated prothrombin, we can actually do a couple of things. Thrombin's going to have two major effects. It's going to activate fibrinogen. Fibrinogen is inactive. Some of you might have it on your list already under blood cargo because it is a plasma protein. And it's going to activate fibrinogen into fibrin, which is a fibrous protein that's going to get laid down over our clot, okay? Over our gel-like blood, over our platelets, over any erythrocytes that are trapped in there, okay? However, these fibrin threads, if you will, they're not cross-linked. So this could be a more stable clot. Probably should not have used that word, and I'll tell you why soon. And therefore, thrombin is also, not surprisingly, going to, with the assistance of calcium, activate factor 13, and activated 13 cross-links fibrin threads and turns this from some less sturdy parallel strips into a mesh or a network. It's now more or less one unit, one blanket, rather than lots and lots of strips of yarn. Okay, so ultimately, what we're going to get out of this step 3C is fibrin mesh. And now, finally, we get to say, clot! Yay, we have a clot! Woohoo! All right? Now you might think, okay, thank goodness we're done with that stupid hemostasis thing. Oh no. More steps. Don't you worry about that. Just in case you need the visual assistance, here's what we just called 3B. Okay, and again, its yield is activated thrombin. And here's what we just called 3C, and its yield is fibrin mesh. Okay? All right, well, we've got a clot. Yay, we have a clot. Okay, but we're actually not done with this whole process because we can't just leave a clot sitting in a vessel. That's potentially dangerous because it acts as an obstacle, which we talked about having a deleterious effect on blood flow, right? So after forming the clot, after coagulation, to stabilize the clot, which really kind of means squeezing any fluid, specifically squeezing serum, out of the clot and making the clot as contracted, as small as possible. Okay? This actually acts like tightening stitches because it helps to bring damaged edges of vessel wall together. So imagine pulling on a thread to tighten stitches. Okay, and this happens, this clot retraction or stabilization, same thing. It happens within 30 to 60 minutes of damage. So that's very, very fast. Very fast. By the way, serum is simply plasma without clotting factors. Okay, but we'll come back to that. Or serum without plasma proteins. You can think of it that, or plasma rather, without plasma proteins. You can think of it that way. And then the other thing that has to happen after we form a clot, we got to get rid of it. Believe it or not, right? We went through all of that effort to make it. Well, ultimately, we want to get rid of it. We don't want obstacles building up inside our vessel walls. That's so not safe. So, even while clot retraction is happening, so simultaneous with clot retraction, the vessel, the underlying vessel, is healing. And one of the things that really promotes the healing of damaged smooth muscle, really damaged blood vessel wall, is platelet-derived growth factor. And you might remember that near the end of 17A, I said, hey, maybe if this could ring a bell later, that'd be great. This is just one of the chemicals that's released by platelets when they become activated. So really, vessel healing starts very early, even before we're totally done forming the clot. Okay? Believe it or not, yay! Just because we've repaired, we've healed the vessel, we still haven't removed the clot, all right? And removal of the clot is called fibrinolysis. Fibrinolysis, okay? It begins within 2 days of clot formation. So not within 2 days of this, but within 2 days of this, right? Within 2 days of I just realized you can't see what this is. The termination of coagulation, okay? So this is happening in conjunction with clot retraction and vessel healing. And it typically takes several days until the clot is fully dissolved. Fibrinolysis is dependent on the plasma protein plasminogen, which is another plasma protein that I think many of you have listed separately under your massive list of blood cargo. Plasminogen gets trapped underneath that fibrin mesh, even underneath the platelet plug for that matter, within a clot. And that the trapping of it is what helps to activate it. So plasminogen is inactive, and its activated form is plasmin. And plasmin, not plasminogen, but plasmin, actually breaks down fibrin. And so this plasmin is getting to work to break down fibrin essentially as soon as we form it. So we're trying to get rid of the clot as soon as possible. It's very temporary. It's less temporary than a platelet plug, but still temporary. We ultimately want to get rid of it. All right. Now I've said this before. Hey, we experience damage in our vessels all the time. That's normal. It's normal to experience damage in vessels, especially the smallest vessels. They're just going to come into contact with more particles within the blood, and we form clots to respond. Well, if we didn't complete this very last step, fibrinolysis, then clots would just accumulate, and our smallest vessels would eventually become blocked. So because damage is a normal thing, clotting is also a normal thing. And because clotting is a normal thing, then fibrinolysis is also a normal thing. It's a routine process that we're all performing all the time. You need to be able to outline the entire process of hemostasis, all the way from vascular spasm through fibrinolysis, okay? And again, I'll show you in class a model. However, in class, I'll flash the model before your eyes. You won't have time to really inspect it. The only way to gain access for an extended period of time to the model is to come to office hours. Okay? And again, if you can't come to office hours, always make an effort to study with someone who can. Get access to someone who can come to office hours so that they can tell you what we did. They can show you what they may have generated during the office hours. So gain access to office hours one way or another. Can't emphasize that enough, especially considering our latest snow days. All right. Yay, even more blood disorders. Specifically, we're going to talk about some disorders of hemostasis. What happens when hemostasis doesn't proceed the way that it should. And sometimes we will, surprisingly, form clots without damage, without blood vessels becoming damaged. And when that happens, that kind of clot, that sort of like uncalled for clot, it's called a thrombus. A thrombus, okay? And obviously, a clot any clot, whether it's meant to be there or not, whether it's unintended or not, it can act as an obstacle, right? An obstacle means impaired blood flow. Potentially. Okay, so thrombus, no thank you. If I cannot have a clot, then I'll opt for that. But certainly if I have damage, then a clot is necessary. But if I don't have damage, then good grief. Let's skip the clot part. Now, a thrombus can not only potentially impair blood flow, but it also has the at least possibility, if not capability, of eventually breaking away from the vessel wall and therefore entering the bloodstream. And if a thrombus breaks away from a wall and enters the bloodstream, that thrombus is now called an embolus. An embolus. If an embolus enters a vessel whose diameter is as narrow or even more narrow than the embolus itself, we then call that condition an embolism. An embolism. And an embolism is not quite the same thing as an aneurysm. An aneurysm is a case where in the process of forming an atheroma, the blood vessel balloons and even ruptures. An embolism doesn't necessarily cause a blood vessel to rupture, okay? But like aneurysm, embolisms are tied to atherosclerosis. The greater the risk of atherosclerosis, the greater the risk of embolism. Inflammation is also a risk factor. Sluggish blood is a risk factor, well, really for so many things. And one reason why we might feature sluggish blood, obviously, is a change in viscosity, but also if we have a patient who's immobile for an extended period of time, then the blood could pool, at least in certain regions of the body. So that's one of the reasons why following surgery, often there'll be a cuff applied to a patient's limbs just to work blood back to the heart, because the patient is immobile and isn't actually milking the blood through the venous side of circulation as much as they would if they were up and around. Okay. Next thing we're going to talk about is blood centrifugation. Oh my goodness. Blood centrifugation. There, I got it. Howdy. Sometimes we want to isolate from a patient plasma. Sometimes we want to isolate from a patient serum. And sometimes we want to isolate both from a patient. So either way, we're going to start by drawing blood. Hopefully that's obvious. But sometimes it's so obvious that when students are taking an exam, if they're asked to describe how to isolate plasma or serum, wink, wink, nudge, nudge, they forget to mention that part, which is just silly. Obviously, you can't isolate plasma or isolate serum for a patient if you don't draw blood from the patient. So make sure you include that step. The key difference, though, is that when we isolate plasma from a patient's blood draw, we're drawing blood into a test tube that's already got anticoagulant in it, okay? Whereas when we're isolating serum from a patient, maybe the same patient, we're drawing blood into a test tube that is not already pre-treated with anticoagulant, but is pre-treated with serum separator gel. So a test tube that's going to isolate plasma, pre-treated with anticoagulant, a test tube that's going to isolate serum, allow us to isolate serum, pre-treated with serum separator gel. All right? Well, if a test tube is pre-treated with anticoagulant, then that means that the blood can't clot. And the reason why that's relevant is that glass is actually a negatively charged surface. So if blood comes into contact, or really platelets come into contact with glass, like the glass of a test tube, then clotting can be initiated. So we don't want clotting in the case of plasma isolation. We don't want a clot to form. We want the formed elements to stand apart, if you will. Whereas if we're isolating serum, well, we're trying to get clotting factors out of the plasma. So we want to allow a clot. Okay? In either case, after we've drawn blood into this pre-treated test tube, we're going to centrifuge that test tube. And then we're going to carefully either pour off or pipette off from the top the fluid. And the fluid on top of the buffy coat, or above the buffy coat, in the case of the plasma draw, will be plasma. The fluid at the top of the test tube in the case of a serum draw will be serum. And the serum will sit above kind of a wall that's made out of serum separator gel. Okay, and then we transfer that fluid, whether we're transferring plasma or serum, via pipette or by pouring, into a separate sterile test tube. And now we can say, hey, I isolated plasma, or hey, I isolated serum. Typically, pipette is used in either case. But serum, because it's separated from the clot by gel, can be poured. Okay, personally, you already know this. I'm a visual learner. I didn't learn anything from that slide. I need a visual slide, so I need the next slide, the slide that actually has images shown. Now, I could not find an image that showed both serum and plasma isolation before and after to save my life. So I had to patch this one together, which is pretty clear. It's a hot mess. It's pretty clear that I had to patch it together. So bear with me. On this side of the slide, this is before we centrifuge. Okay, we've drawn the blood into a test tube. This particular test tube, the one with the red cap, it has anticoagulant already in it. So that means that this is going to be the plasma specimen, right? Whereas this tube, the one with the blue top, it doesn't have anticoagulant. Instead, it has the pretreatment of serum separator gel. So this is going to be our serum sample. Now we're going to centrifuge these, okay? And here's our result. We've centrifuged the tubes, so you can keep these cap colors together, where red is going to mean plasma, all right? And blue is going to mean serum, and often these are the colors that are used clinically. in the plasma specimen, what do we get? We get plasma on top, which includes plasma proteins, including clotting factors. We're going to get our hematocrit, our erythrocytes at the bottom, and in between the two, we're going to get buffy coat. Okay, and what do we want to isolate? We want to isolate this kind of sticky, straw-colored fluid that's on the top. Okay, the best way to get it out of there is to really carefully pipette it out of there, or aspirate it. That's the same thing. All right. Whereas in the serum draw, what we have is serum on top, clot at the base in the bottom, which is obviously going to include the clotting factors. So by allowing a clot to form, we've also drawn the clotting factors out of the plasma and yielded serum without clotting factors. And in between the two is our separator gel. All right. So what do we want from here? We want the fluid that's on top. Right. We can pour it because the gel doesn't allow the clot to pour out, but probably the safest way to get the serum out of there is to carefully pipette it out of there. All right. So serum versus plasma. Blood groups. We already know that cells in general wear lots and lots and lots and lots and lots of name tags. And those name tags are called antigens, right? Our own cells feature self-antigens. And then any foreigner will, or any foreign cell, I should say. That didn't sound right, did it? Will feature, obviously, foreign or non-self antigens, okay? Well, red blood cells, erythrocytes, are no exception. They have antigens, name tags all over them. And in fact, they have hundreds and hundreds of antigens, but there are about 30 different types of antigens, 30 different types of name tags, or 30 different types of identifiers, okay? Now, in our own bodies, our self-antigens, hopefully, don't initiate or trigger an immune response. But by definition, an antigen is anything that could generate or trigger or stimulate the immune response. So if we put antigens from our body into another person's body, yes, our self-antigens could be perceived as non-self. In fact, they're likely to be perceived as non-self in another person's body, and therefore could initiate or trigger the immune response in that other person's body. So that's actually why talking about human blood groups is going to be relevant, because we're going to talk about transfusions. Well, the antigens that are worn, if you will, by erythrocytes, it can just be called erythrocyte antigens, but they're also known as agglutinogens, because if they're triggering an immune response in a non-self body, then they promote like a clumping that is called agglutination. Clumping. And I'm going to just hop a couple of slides, 3 slides? Yeah, 3 slides ahead to an image where we can see agglutination. We can see agglutination. So this is clumping, this is clumping, clumping, clumping. Okay, agglutination, clumping. Well, as you know, we don't want clumps of things in our blood because that affects viscosity and therefore impairs blood flow, so no thank you. And that's why it's so important when transfusing, there we go, blood, or even when a person becomes exposed, a person at risk becomes exposed in an at-risk way to another person's blood. Why it's so important, if possible, to match donor and recipient blood to minimize the risk of agglutination, of clumping. All right, we don't want more viscous blood. We don't want to have to wait for macrophages to arrive and destroy that blood. And frankly, if someone's getting a transfusion, they're already in trouble. So, having their already compromised body, having to deal with this clumped blood, and having to send macrophages to clean all that up. What a horrible mess. But we'll come back to that soon, or again, I should say. So again, there are about 30 different types of name tags, if you will, that erythrocytes wear. And for most of the types, we simply address whether the antigen in question is present or absent. So is the red blood cell wearing this name tag or not wearing this name tag? And some of the blood groups, some of those 30-ish blood groups or 30-ish different types of name tags include some really weak name tags that are not likely to trigger an immune response or not likely to trigger a strong immune response. So we don't worry so much about the weaker blood groups. We worry about those that bring about really strong immune responses, really strong transfusion reactions. And those are the ABO blood group and the RH blood group. The ABO blood group and the RH blood group. Okay, those are the two that we worry about most in the case of transfusion or in the case of a patient becoming exposed, or an at-risk patient becoming exposed in an at-risk way to another person's blood. When we do transfuse blood, typically we transfuse hematocrit only, so we take buffy coat and plasma out of the mix and transfuse just what are often referred to as packed erythrocytes, often because the patient's own hematocrit is low and that compromises their oxygen carrying capacity. If a transfusion occurs, it's so important that you understand what's happening. The donor's cells, those cells that are donated, are being attacked by the recipient's antigens or agglutinogens, okay? Now, here's one way to think of it. Let's say that this box represents the 5-ish liters of blood, okay, of the patient, meaning the recipient, all right? And let's say this small box represents the amount of blood coming from the donor, okay? Well, which box has the greater impact on the other? Is the small box going to have a huge impact on a much bigger box? Or is the much bigger box going to have an impact on the much smaller box? Well, the much bigger box has a much bigger impact. So it's always a case, in the case of a transfusion reaction, it's always a case of the recipient attacking the donor's blood. Not inside the donor's body. It's already been removed from the donor's body. But the recipient attacking the donor's blood. All right? We don't worry about the donor attacking the recipient's blood because it's such a small contribution. The reaction would be so minor in the opposite direction, that it is not worth consideration. Okay? Well, the recipients antigens, the agglutinogens, will, if mismatched, clump to the donor cells, okay, cause agglutination, right? And that's an issue for blood flow. It also greatly increases the likelihood that those donor cells will rupture and release hemoglobin into the bloodstream, which also impairs, I should say, blood flow. Okay, and as a result, the patient, the recipient is likely to feature an even more diminished oxygen carrying capacity. Well, we're talking about a patient that was already in trouble, right? If you need a transfusion, you're already in trouble. So why on earth would we want to put a patient who's already in trouble into this situation where their oxygen carrying capacity is even more so impaired? That's potentially life-threatening. Also, the viscosity of the blood can block vessels. Hemoglobin, now exposed in the blood, can cause renal failure in the kidneys. Just bad news. No, thank you. So excuse me. Prior to a transfusion, it's important that we type blood, that we determine the blood type. Specifically, we're concerned again about ABO and RH blood types of both patient and donor. And one of the ways that we can determine that is by mixing patient blood, mixing donor blood with like synthetically made agglutinogens and observing for clumping. Okay, so if clumping occurs, then we know don't transfuse. If clumping occurs on a petri dish, then that means clumping is likely to occur in the patient. So no thanks, meaning the recipient. Don't transfuse. And we can really do that same thing, that mixing of blood with synthetic agglutinogens on a petri dish, really, or even a slide, for both ABO and RH blood types. When we have a specific donor and a specific recipient, so that we can draw blood from both, then we can mix the recipient's serum, and we know now how to isolate serum, with donor erythrocytes before actually performing the transfusion. We can mix the recipient's erythrocytes with donor serum, and we know now how to isolate serum again to look for clumping. Any clumping? If there's clumping, don't transfuse. Okay. Again, what matters is whether the recipients. Oh, I actually misspoke earlier. In fact, I'm going to do this lecture again. Okay, so I'd like to go back to specifically the whole blood transfusion slide, because my mouth made a mistake, and I want to make sure that you can follow along. We talked about transfusing packed red blood cells. We're good. We talked about transfusion reactions being very bad news, especially because the patient is likely already compromised. So why would we want to compromise someone that's already having trouble? But the thing that I really failed to point out here is this term, agglutinins. Agglutinins and agglutinogens are not the same thing. Agglutinins are the patient's, the recipient's antibodies. And my mouth said that the patient's agglutinogens will attack donor blood. No. The patient's or recipient's antibodies, also known as agglutinins, will attack mismatched donor blood. So I just wanted to make that correction because this is already tough stuff, and I don't want to make things even worse for you. Agglutinins, sorry that it's so similar to agglutinogens, are antibodies, and of course are most relevant in the recipient blood, whereas agglutinogens are going to be most relevant. How about I spell that correctly instead? Agglutinogens are going to be most relevant in donor blood. Agglutinogens. There we go. Okay. Anywho, let's see. I think that we did start the determining blood. Yes. We talked about the determining blood type slide. In fact, that's where I stopped lecture and went back to make this next recording. And here I think my mouth also said possibly agglutinogens instead of antibodies. Antibodies. And again, it's the recipient's antibodies that will attack mismatched donor blood. If it's not mismatched, then no attack, no agglutination. Mismatched donor blood. Okay. And antigens here is the same thing as agglutinogens. All right. Okay. In the next slide, where we have the photos of some blood that is agglutinated, we can see that there's a strong difference, a strong contrast between clumped and non-clumped blood. So that means that there's a clinical way to easily observe whether or not blood will likely clump. Moving on to ABO blood groups. There are 4 types of ABO blood groups. Type A, Type B, Type AB, and Type O. And you've probably heard of all of them in the past. They are based on, again, whether or not apps are present, the antigens, the agglutinogens A and B, or I can even say A or B, are being worn by red blood cells, And the body, depending on what types of agglutinogens are worn by self, may make agglutinins, not to be confused with agglutinogens, which again my mouth did just recently because I'm a jerk. I'm so sorry. And those agglutinins are potentially anti-A antibodies. Yes, you have to say anti twice. Yay! And or anti-B antibodies. Yes, you have to say anti twice. Okay? If our recipient's blood, for instance, produces anti-A antibodies, and we transfuse donor blood that does feature type A agglutinogens, then the antibodies, the anti-A antibodies of the recipient will clump with the type A agglutinogens of the donor. And again, that's not an option. This table is really, really handy, really helpful for kind of laying out all of the circumstances, okay? So here we're looking at red blood cells, and obviously just some ABO of the name tags that those red blood cells may wear. In this particular first red blood cell, we can see, oh, this red blood cell is wearing the name tags A and B. A and B. If this were, for instance, recipient blood, so this is an RBC in recipient blood, and therefore all of the erythrocytes are wearing both A name tags and B name tags, then the recipient would be wise to not make any anti-A or anti-B antibodies, right? The recipient isn't going to make antibodies against itself or themselves, okay? So that means that if someone has the ABO blood type of AB, they have both A and B agglutinogens, but neither anti-A nor anti-B antibodies, also known as agglutinins, okay? If we march along to the next example of a red blood cell, we can see, oh, this red blood cell is wearing, at least where ABO blood types are concerned, wearing only the B antigen or the B agglutinogen. Okay, so the patient is not, or for this person is not going to generate any anti-B antibodies, because if they did, they would attack themselves. Okay, but because they don't wear the type A name tag, they are going to generate and feature in their blood anti-A antibodies. Okay, this person is said to have type B blood. AB again, erythrocytes wear both A and B. B again, erythrocytes wear only B. Okay. In this next example of an erythrocyte, we can see, oh, okay, so this erythrocyte wears, at least for the ABO blood type, only type A name tags, right? It's not, this patient isn't going to generate anti-A antibodies, because they would then attack themselves, so we're not going to see that antibody. But because they don't themselves wear the type B name tag, they are going to make anti-B antibodies. Okay, this blood type is called type A. Okay, notice in our last example here that erythrocytes wear neither the A or B agglutinogen, neither the A or B name tag, okay? Therefore, if this person were to make anti-A and anti-B antibodies, well, they wouldn't be attacking themselves. So sure enough, someone with type O blood will generate both anti-A and anti-B antibodies, okay? Whereas someone with both A and B agglutinogens on their red blood cells will not generate any of the anti-A or anti-B antibodies. So a lot of people think of A and B as almost opposites. And you may already consider type O to be the universal donor and type AB to be the universal recipient. Why? Because type AB isn't going to attack any donor's blood, whereas type O is not equipped with agglutinogens. There we go. To trigger a transfusion reaction in a recipient. So it can be donated to any patient. And then here, I don't need you to memorize at all this demographic information, but it's kind of interesting to see which blood types are most common, which are most rare. And the most rare blood type, can you already tell? Type AB. Okay, so moving. Oh, one thing I wanted to point out actually before I move on to the next slide. We start making and accumulating anti-A and or anti-B antibodies if we're going to make them. And of course, if we have type AB blood, we're not going to make them. But if we're going to make them, we start accumulating them at about 2 months of age. We don't make all of our antibodies at the same age or at the same moment in our lifespan. So that's something to keep in mind. And our anti-A and anti-B antibodies, they haven't reached our sort of adult levels until we're maybe 8 or 10 years old, 8, 9, 10, somewhere in there. Okay, so keep that in mind. There are something along the lines of 52 different RH agglutinogens, whereas when we're talking about ABO blood types, there were just really 2, A and or B. This is like saying there are 52 different things that we could write on an RH name tag. And some of the things that we could write on an RH name tag are nicknamed C, D, E, and so forth. And those three, C, D, and E, are the most common sort of, I guess, names you might see written, analogy galore here, on an RH name tag, okay? But when we talk about someone's RH factor or RH type, we're really talking specifically about whether they have the name, if you will, D, written on their RH name tag. So when we say someone's RH positive or RH negative, we're really worried about or concerned with what their D group is looking like on their erythrocytes. Okay, and most people, more people than not, they are RH positive, which means that they do feature the RHD agglutinogen. They do, okay? Whereas if someone's Rh negative, which is less common, right, then we mean that their RHD name tag, we could say that they either don't have that name tag or it's blank. Okay, so if someone's Rh negative, then they do not feature the RHD agglutinogen. Okay, well, sort of feeding off the principles that we just learned by going over the ABO blood type, you can probably infer someone, I'm going to separate these, someone who does feature the RHD agglutinogen isn't going to make anti-RHD antibodies. Because if they did, they'd attack themselves, right? Whereas someone who doesn't feature the RHD agglutinogen, it's absent, if they were to make anti-RHD, of course, antibodies, hey, that'd be okay. So, yes, antibodies, because they're not going to attack themselves. No antibodies. All right, that's important. Okay. So, we just established this. People that are Rh negative, they may form antibodies. However, they don't form their antibodies spontaneously. Whereas, in the case of ABO blood types, antibodies are generated spontaneously. Okay, so this means that someone who's Rh negative, they're not going to generate, even though they have the capability, they're not going to generate anti-RHD antibodies unless they're exposed to the RHD agglutinogen. Okay, how might someone be exposed? Well, they might be exposed via transfusion. They might be exposed via pregnancy. Well, really, delivery. Okay, so we're going to use this image to help us along. Here's a papa, and it just so happens that this papa is Rh positive. Okay, and here's a mama, and it just so happens that this mama is Rh negative, and of course we mean RHD. Okay. Well, if we have an Rh negative mama and an Rh positive papa, is it possible that that baby, fetus, could inherit the Rh positive condition? Absolutely. But is it also possible that baby, fetus, could inherit the Rh negative condition? Absolutely. Sure. Okay, but in this particular scenario, we're going to say that this fetus inherited from papa. So the fetus is a little tiny, Rh positive. Okay, well, before pregnancy and even during pregnancy, mama has likely not been exposed directly to baby's blood. Okay. But during labor and delivery, there's going to be exposure, and certainly by the time we're in labor and delivery, baby's blood is very fully developed, and erythrocytes are wearing all the name tags that, or at least many of the name tags that they're going to feature. But the take-home message here is that over the course of pregnancy, mama, who is Rh negative, simply doesn't have enough time to develop anti-Rh antibodies. Okay, whereas following pregnancy, so baby's out. Okay, mama has time to form those antibodies, and that's what these little green guys are. These are antibodies. So mama's Rh factor hasn't changed. In fact, there's no way to change it. She's still Rh negative, okay? But now, over time, she's developed antibodies. She didn't have antibodies during this first pregnancy, okay? But now, later on, she's had enough time to develop antibodies, okay? So if this same papa and this same mama, who now has not only the Rh negative condition, but features anti-Rh, obviously D, antibodies, if they make another baby, and that baby also happens to inherit Papa's Rh positive condition, well, Mama's now got antibodies, okay? And these particular antibodies, not that all do, but these do, they can cross the placenta and attack the red blood cells of the fetus. So this is second pregnancy, and this second pregnancy, is threatened. Okay, so what do we do about this? Well, at least in the U.S., when a pregnant mama visits, hopefully on a regular basis, the doctor, we very early on sample Mama's blood and find out what her Rh group is. Is she Rh positive? Is she Rh negative? If she's Rh negative and she's never been pregnant before and she's never had a transfusion and she doesn't have, therefore, any anti-Rh antibodies, then what we do is either during delivery or right after delivery, or sometimes even both, we treat with something called RhoGAM. And RhoGAM is essentially a medication that tells Mama's body, hey, you don't need to make any of those anti-Rh antibodies. You just thought there was an Rh positive fetus inside of you. Everything's fine. Don't worry about it. Okay? And that means that Mama, even later on, isn't going to make those anti-Rh antibodies so that the second pregnancy can proceed. Okay? But yes, during that second pregnancy or any other subsequent pregnancies, if we have Rh negative Mama, we're going to treat every time with RhoGAM. Okay? Okay, so what's the take-home message for all these horrible blood group particulars? Well, I can give you any scenario where I tell you what the donor blood has and what the recipient blood has. And I may or may not, in terms of blood types, okay, and I may or may not tell you what the recipient's history is, okay? And not only will you have to identify whether you predict a transfusion reaction will occur, but you'll also have to be able to explain why or why not. And there are a number of examples on our last slide, slide 28, that we'll work through in class, okay, just to get some practice. If you need more practice, let me know. I can provide that very, very easily. Anywho, there's lots and lots of lecture. Woo!